OK. So I come from the Institute for Artificial Intelligence, as was said, and in the consortium with the Bayer company, we did NGI search project that we got a grant for in September last year. About doing this project that's called VerifAI that had intention to a bit deal with the hallucinations that the generative large language models are making. So we just heard a lot about those hallucinations. And generative LLMs can produce answers that appear coherent, confident, and even articulate. Even though they can be only like statistics and frequency stuff, they, to us, like from the practical approach, look like language. And they have a complete grammatical structure, so they're syntactically and semantically correct. They even can have the pragmatic language level OK, but the correctness of that answer can be problematic. So that can be a real problem in like various aspects, but especially in some sort of like important live fields like biomedicine, where you can, by like trusting them, have severe problems. And also, if you're using some sort of third-part APIs and you're working in pharma or some other sort of biomedical company, then you may have a problem because of the privacy of information, about the ways of payment, and so on. So we wanted, in this open source approach, to deal with that. Like generative large language models make the next token prediction, and they are based on large amount of data, so they know a great deal of stuff, but they are trained up to the point in time, so they don't have like current information. And also, in the process of obtaining the data for the LLM training, they could like have some information that is missed. So there is an approach that's called Retrieval-Augmented Generation. That means that you have some sort of external data that's not seen by the model training, and that with that, you can augment that model, fine-tune it, and then get like the more, perhaps more correct, factually correct answers. And also, it's important to provide sources for that data, because even then, you're going to have some sort of precision at which your answers are given. But also, we wanted to additionally check that answers. So we did the referencing part also and make some sort of textual entailment model that co-referenced that stuff, and that checked for the correctness of information from the direct sources. So this is the scheme for our VerifAI project. So we have, at the beginning, the user who has some sort of question, and it's put into the prompt for a large generative model. And we have three important and great parts. So first one is the information retrieval component. The second one is that generative component. And the third one is the sort of fact-checking or verification engine. And I will explain all of them in the next slides. So first, the information retrieval system. It has to retrieve relevant articles for the questions that the user is putting in the model. Because this is field of biomedicine, we considered PubMed repository system because it has almost 40 million articles that dates way back before the mid-20th century. And also there is a great deal of metadata. For example, the names of authors, journals, medical journals, they are published in years and some other of aspects. And they have the unique PubMed ID, and they also have links to the full papers. And we didn't consider the full papers because they are too long to go as an input in the model. So we wanted to do only abstracts, but then on the previous project we realized that the titles have a lot of information that should be used. So we made a sort of concatenation from titles and abstract of each of that. On that PubMed repository, there was a great deal of empty abstracts. So we finished at about 25.5 million of abstracts. And because there are some sort of logistic limitations in the models that we are going to fine tune, and that was like the maximum input size of around 500 tokens, then we decided not just to truncate that title abstract concatenation because we thought that that would lose some sort of very important information. So we did a text segmentation, and they all have some sort of different indexes when we did the indexing, but all the segments from the same title abstract concatenation have the same PubMed ID so that we can reconstruct them if needed. In the literature and in the practice, there are like 3 ways to deal with the information retrieval, to deal with some sort of search. So we first did the lexical search that incorporates like finding the exact matching keywords, and it's sort of sparse vectors that we are dealing with. We concretely did the BEM25 because it's better than just ordinarily doing term frequency inverse document frequency matrices. And we also indexed the metadata, and concretely author's name, years, and journals, because we think that like the user would like to make some sort of filters in our user interface that I will show you at the end. And we did the lexical indexing based on OpenSearch vector database. Because lexical search can only deal with like exact matches or some sort of normalized exact matches, we also wanted to include semantic search. And semantic search enables us to search for the synonyms and for the paraphrases that can mean the same thing but in different words or different language constructions as the ones that we want to find. And you do semantic search in various ways, but our approach was to deal with the asymmetric semantic search because we understand that our users' queries can be long questions, can be just a few words, or can be some sort of a statement for which he wants to find some sort of answers. And the answers would be a bit longer. So what we wanted to do is to represent the query into some sort of dense vector and had all of those 25 million abstracts represented as vectors, embeddings, and then do like the comparison and concretely do it with the scalar vector product because they are of a different size. We used for this part the quadrant vector database, and we did it on the by encoder because we had to compare the 2 instances. It took some time on our AWS server to do that, so that the part with the vectorizing embeddings of those abstracts was done offline. And each time our user, through the user interface, gives a query, it's online transformed, then compared, and we get back the answers. And then we wanted to have the both ways in our final search, so we combined them in sort of hybrid search. And in order to do that, firstly, we had to normalize them on the same scale. And then we did a series of experiments to see at which weights of lexical and semantic search should be in our final product. And I'll talk about that a bit later. And we did an evaluation of our system on BioAsk dataset because it's a benchmark dataset in this field, and the results I will show later are based on that. Then we have a generative component, and generative component receives the information from the information retrieval, and then utilizes them to find a sort of fine-tune generative LLM. So in order to fine-tune a generative LLM, we first have to have a sort of data set, and we decided to make our own, sort of. So we randomly selected about 9,000 questions from the PubMed question Q&A data set. And then based on their PubMed IDs, we extracted for each of them 10 relevant abstracts from PubMed repository. And then we gave the GPT-4 that's scored the best correct chat model at the moment that we approached this problem. And it gave us back the responses that were referenced for that. And so sort of we made that data set. And then this data set was used to fine-tune the instruct version, 2 instruct versions of Mistral that had 7 billion parameters. So those 7 billion parameters was the problem for us because we only had a single GPU to use. And then we had to deal with that. So we first tried with LoRa methodology, so low rank adaptation methodology. For those of us who maybe don't know, it's a simplification that that can bring much smaller amount of memory that's supposed to be used. So, for example, if we need to update our weight matrices and it's 5 times 5, so it has but it's not, it's much bigger. It has 25 parameters. What we can do is make it into sort of vector or matrix multiplication, 5 by 1 and 1 by 5, so we actually would have 10 parameters instead of 25 parameters, which is maybe not look like the big difference, but if you have a matrix weight matrices that's 500 times 500, then you have 250,000 parameters, and if you low rank it, then you would have only 100 parameters. But that still wasn't enough, so we then did the quantized LoRa or QLoRa, and we actually get to use it on our one GPU of 40 gigabytes with those parameters, and that reduced the model size of only 27 million trainable parameters. It took us 32 hours to train it for 2 epochs, and our batch size was only 1, but we are now trying to obtain another GPU and to maybe make that a little more. Okay. And then we had the third part of our system, and that's the verification engine. So we decided that our verification engine should be sort of simplified to be like a textual entailment task. And for textual entailment task, you have pairs of segments, and you actually do a classification, in our case, on 3 classes. So no evidence when we cannot find some concrete evidence for the answer in those claims, contradict, or support. And for that, we used the CFAC dataset, but we had to additionally transform it because it's not publicly available for the whole part. and we had to do the train validation and test split, and we also had to reduce the size of some things, and also to be like the same with the approach we use to do that with the title and abstract concatenations. So we make the like transform data set and then train on a various models to obtain the best results, which I'll show in a minute. So these are the results for our information retrieval system. We tried with the lexical approach, so lexical search, and we compared our search with the original PubMed engine search, and we can see from the like line 12, and then afterwards that we are getting much better results on mean average precision at first 10 retrieved abstracts. We also did separately semantic search, and it's like okay result, either it's a bit low, and then we did the hybrid search for like the all 9 other combinations of the parameters, and concluded that this is like the best combination of weights for lexical and semantic search for our approach. And we compare with some sort of benchmark data setting, and we have an absolute increase of 9% compared to them. For the generative component, we train on like version 1 and version 2 of Mistral 7B Instruct, and we compared those results with ChatGPT Turbo, which is like a much larger model, and you would like need so much more memory and stuff to train it, and it's also not free and not open. So if you like want to use it for that, you have to pay that. And we concluded that for some stuff that's important, like for the process of obtaining the answers, our models, so the model that's based on Mistral 7B version 2 and fine-tuned on our model is the best one. And for the verification engine, we actually tried quite a bit of models, and this is like only the 4 that I'm presenting here. We tried to deal with sort of parameters when, for example, the early stopping for the dropout, so now to overfit was the most interesting, so I'm presenting it here, and find out that actually the Berta model gained the best performance when we validated on like 10% of our transform data set, which we like left for that. And then we also like wanted to have additional check and did like sort of outbound evaluation on the healthware data set. And these results that are on the on your right are actually almost 10% has the absolute raise from other models that are currently or was state of the art. And then we have like finally got to our user interface because we are working on this for like 8 months now. And we did the demo. So our user have a question, and then it inputs it in the system that goes through some sort of pre-processing, and then goes into information retrieval system, and done by both lexical and semantic search. And we get the result of a hybrid search. These 10 abstracts, that's the best based on hybrid search, are returned to our fine-tuned Mistral model, and then it gives us some sort of like generated answer. And that generated answer for almost each sentence has a PubMed ID reference, so that in our like third part we can fact check for that. So then it gains like the final step is that you have the claim from the generative model that's paired with the concrete abstract from our retrieval system, and it defines is it support, contradict, or no evidence, and then the user gets verified, checked, generative answer from that model. So we even have the, for now, very basic site where you can freely log in if you want, and you would have sort of like this tab where you can choose between hybrid, semantic, or lexical search. And if you choose hybrid, then you would have to put like those weights. This is just represented with the best weights that we have so far. And you can, because if you want like to have more current data, then just put the dates like from which you want to get your abstracts from PubMed database, and also set the temperature. We set it here for precise, and this is actually, I couldn't catch, like the first thing is all gray because you just like get the generated answers with those PubMed IDs, and afterwards it's coloring it. So, for example, the green color means that it's supporting, and if you hover over it, you can even see like the sentence from that concrete abstract of PubMed on which the current claim from the generative model is based, and also you'll have a link to go to the full paper if it's possible in some sort of PubMed Medline repository. So I think that's it, not to like talk anymore. Yes, we also, because this project is at the end, we have some stuff to do, but we like gained so many new perspective on that and would like to do like some new stuff. And also we would like to have, if you have some like back information that we maybe can approach this a bit differently or improve it. So we also try to get funded for the like broadening the spectrum, not only on biomedicine, but for now for the whole scientific community, and to where we can put those new things that we find out about, and to broaden that perspective, and maybe then do something more with that. And like we would like to foster the trust in generative AI across various scientific domains. So thank you for your attention. That's it. If you have some questions.
Hi.
Sorry?
Okay. Can I now ask? Thank you for your talk. It was really interesting. I wanted to ask, how do you tackle the need of updating the articles? I'm here.
Sorry, I don't see you.
How do you tackle the need of updating the articles? So like, or do you at this point want to keep the database of your articles copies intact?
So those like
5
million abstracts was like the historical data, and we each month obtain new articles because PubMed repository is updated monthly, and then we also like did the vector embeddings for them in each month and add them to that offline part. So each new month, if you search for it, you would have more current articles.
So the new articles are the new embeddings?
Yeah.
Okay.
Once monthly.
Monthly. Okay, thank you so much.
Okay, I have a question. So basically, more and more of published documents are today at least partially generated by LLMs. And also, as you know, some of the published documents are simply not valid. So do you have, let's say, scoring of inputted documents? Do you check it if they're generated by LLMs?
In this use case, no, because this is like the PubMed is a repository that's obtained by National Library for Medicine of American Society, and it has only the articles for like Web of Science corpus, so the peer-reviewed articles that have checked for like grammatical errors, for logical errors, for stuff like that. So we think of it like a referenced stuff. But when you gain the answer, you have also the access to the concrete publication, so you can check for the authors, for the impact factor of that article, and if you want, read the whole article and see if that's something that you agree on, because like it's the factuality of the repository that can be like put to question, but then that's completely out of scope of us and put into the hands of the concrete researcher or company or stuff like that. So we have it like transparently from which source, which year, which article, blah, blah. It's like derived, if that answers your question.
Partially, yes. So basically, you understand that, let's say you have a number of published documents related to a certain area. Okay, and
sorry, I haven't, what?
So if you have more documents published regarding, let's say, certain area or subject,
Okay.
and what is a difficult task is to find collision and collisions between published documents. So basically, okay, you cannot take as a ground truth conflicting facts. So that is, let's say, where large language models would help. So basically, you get answers based from published documents, but you understand that even if it is peer-checked and anything, you still have, let's say, published documents which are in collision.
Yeah, but that's not like the LLM's problem, because if you are a human and you read them, you also like gain your information from those papers. Like they are source of information, so you always have to like critically approach all sources information. But that's like, for me, it's a philosophical question. So this is the information, that like the way to verify the things that are there, because generative models can say stuff that are not according to those papers.
That is not what I meant. So basically, it would be helpful to detect conflicting documents. So of course, a large language model cannot say, yes, this is truth and this is false. But it is very difficult to, let's say, even to find conflicting documents. And finding these conflicts, this is something where large language models could really bring added value to the table. So
okay.
It is more of a suggestion. So
okay,
you do.
So now I understand. Okay.
Great.
Yeah.
Thank you.
Thank you.